Hey everyone, welcome to the Resiliency module of our Azure Masterclass V3, because it really is critical to understand all of the considerations, the options you have to enable you to build a resilient, a redundant architecture when using the cloud or even in your hybrid environments. So we're going to dive into the types of resiliency that are available to us, some of the constructs we can leverage in Azure in terms of isolation boundaries when we're designing our architectures, some of the replication capabilities and global balancing options, and then some of the backup type capabilities. So we're going to dive into all of those things as part of this. So first, I want to just quickly cover disaster recovery and what planned versus unplanned means, because there really are three types of disaster recovery. So I can think about planned. And in a planned scenario, it's, hey, look, storm's coming. Let's move our systems over to the DR location before the storm gets here in case there is some problem. This is why a lot of network operations rooms, you'll see they have the news channel on, they have the weather channel on, because those things can impact what they need to do. They have to stay aware of those things. So in this scenario where I see the disaster coming, there should be no data loss that's not expected, and there shouldn't be any unexpected outages, because if I have data, I can cleanly replicate it over to another location. I will have control of when I do that switch over if there was any downtime. So I have control of that. That's very different from an unplanned scenario. And an unplanned scenario is, hey, where did that storm come from and where was my data center gone? In that case, there probably is going to be some data loss, because if your data center just suddenly disappears, well, it didn't have time to copy over maybe that missing data. And I wasn't in control of when that activation of the failover systems was. And chances are there's going to be an extended downtime, because it's a lot harder in those unexpected circumstances to come back to life than if I have full planning over that. And obviously testing is another type. Like, you need to be testing frequently. When there's an actual real disaster, that is not the good time to find, hey, there's a gap in our failover process. And so a lot of organizations will routinely perform a DR process, but additionally, many of them will actually flip over what is the active site and run there for a month. Like, that's really the best way to have confidence in your disaster recovery and know you're not missing anything. Because a lot of times when there's a problem, companies do not want to fail over to the DR site, not just because of, okay, maybe there's a 15-minute downtime. They lack the confidence that their DR location is actually going to work. They don't test it enough. And so if you don't have that confidence, it makes you delay when there's actually a problem. So you end up extending any kind of outage. So you want to have good confidence in your DR capabilities, which means you have to test it. One of the things to also make sure here, though, is, okay, that's the testing, but make sure your DR location, make sure your plan is part of your change control. Think of your DR process as a living document. Your production site has changes. Hey, I changed the resource type. I had in a new application. I changed some config. I update some image. Whenever I'm implementing a change in production, the impact that may have on your DR has to be part of your change control meetings. Okay, we're making this change to this resource. Okay, we're adding this new component. What do we need to update in our DR process to ensure that with this new thing, what would happen if we actually failed over? So what are we actually protecting against? When I think about resiliency, I need to understand, well, what are the different aspects that can actually fail? And that will help me understand, well, where do I actually need to put my various types of mitigation exercise? So obviously the software I can have, and there's different layers when I think of the software. If we kind of jump over for a second, if I think of, well, from a software perspective, well, we have things like an operating system. Now we have the core operating system. The OS can have bugs. The OS can crash. but the OS will have various drivers. And obviously, if it's a kernel mode driver, it can cause the OS to bug check and stop. So that can have a huge impact. I can have various types of agents. It could be a monitoring agent. It could be part of an anti-malware that then calls a driver. But we have monitoring things. We have all of those different components. And I have various types of runtime. Java Enterprise Edition, .NET. I might have various types of middleware. They're all things that are software that I have to update. They can have problems. And then, of course, you have your application itself. And your application, it can have bugs. There might be a client application that connects to it. It can have bugs as well. Now, realize if this is, for example, actually running inside a virtual machine, realize that virtual machine itself is enabled by some other component. For example, I can think back, well, there has to be a hypervisor. In Azure, that's Hyper-V. So that has updates made, that has patches made, that has things happening to it. There are control plane elements. So if it was just Hyper-V, well, then there's the Windows Server running in the management partition. If I'm in Azure, well, there's Azure Resource Manager. There's Fabric controllers. If I'm using PaaS services, there's bits that I don't have any control over, but those get updated as well. So anything software can have bugs introduced that can do many things. It can make it crash. It can make it behave in an unexpected way. It could impact performance. And then, of course, this is running on hardware, and hardware can have failure. If we think about the hardware layers to this, well, obviously, hardware has many different components to it. So now if this is running on a physical box, well, the physical box has a CPU. It has memory, it has storage, it has network capabilities, it has power supply units. This is the host that is either the bare metal OS is running on or the hypervisor, whatever those things are. And typically we have some resiliency built into these. Hey, we have multiple network cards, we might have multiple power supply units, but there are things that can go wrong there. And then, of course, realize this host in most data centers, well, you're living inside a rack. So now I have some particular rack level unit here, and the rack has its own component. So it has power supplies. And again, it would often have redundant, which then feeds into the power supplies of the actual host. I'm going to have, maybe it's a top of rack switch, and that has, again, hopefully redundant connectivity to other things, but that's going and getting connections to other things. Your network, your intranet then goes and connects to other switches. It gives you internet connectivity, connection to private clouds, etc., etc. So there's all these different hardware components and elements that go into this. And the data center has cooling systems and all these other capabilities that all have elements of possible failure. I can then think about corruption. Now, there are many types of corruption possible. This could be because if there was a fault and there's some bad data written. So if I think about, well, corruption where it often hits here is we have our data. Now, it could also corrupt things like elements of the OS, could be elements of a database. A lot of those things now have pretty good capabilities to be resilient to that. But I could have some kind of corruption of my data. Now, I'm saying it could be accidental, some bug, and it could be a failure in something that it accidentally goes and does a whole bunch of updates because of some bug in software. But it could also be an attack. If you think about WannaCry, hey, they go and encrypt those things. Maybe it's a ransomware type thing, and hey, they go and encrypt all the stuff until you pay them to decrypt it. And when you think of corruption, hey, maybe I've got backups. They might try and go after those backups as well. This data could be on shares, it could be local, it could be in a database, there could be many other types of medium available to us. And then I can think about, well, there are those actual attacks. So someone's trying to infiltrate my system, someone's trying to do a denial of service, And if I'm trying to be resilient as a service, well, being resilient means being available. If my service isn't available, well, it's not really resilient anymore. So I have to think about, well, how can I have some kind of protection from those types of things? So here, I can think about, well, there's maybe someone's trying to attack, they're trying to get into my system, or maybe it's a distributed denial of service. They're flooding my service with bad things, and so I can't respond to legitimate requests anymore. So I'm not available. So those are some of the things I'm trying to, from a key point, protect against. Now also, this isn't maybe protecting against as such, but there might be regulatory requirements. This could be based on the country, it could be based on my industry. And depending on the type of service I'm offering, there could be pretty steep penalties, including prison, if I don't meet these. If I'm an emergency service, I have to be available. I can't be down for more than X amount of time. I have to make sure I've got data available for 7 years, for example. And so I have to make sure I'm understanding what those things. And of course, humans, accidental things. If I have insufficient testing and I introduce some change and it destroys or breaks my service, many problems are actually not due to hardware. There's not some piece of component failing. It's because a change was made. And they can seem to be really small changes that have just massive effects. Some of the big ones you see when there's an outage is someone changed a routing configuration. Someone made a change to DNS. I make a change to a database schema. I make a change to software. But they can have these massive impacts that just were completely unforeseen, and they can be really hard to actually undo and protect. So the humans, realistically, we need to try and be able to protect against the humans as well. Now, I want to really quickly touch on the idea of, we have the concept of doing stuff and remembering stuff when we think of resiliency. Now, we're going to talk about a whole bunch of different options on this, but many components are doing one of these two types of tasks for us. So it's good to just really understand what they are. And some of them will do both. So I can think about something that is doing stuff. It's a processing, it's doing compute. They get requests, they perform calculations, they send operations. But they don't have to remember anything, i.e. they have no ongoing state, or at least there's no state I care about. There's no state that I can't just easily recreate, where if I send the request again. Then I have the concept of things that remember stuff. They have a state. They maintain data we care about. It could be a file share, it could be a database. And again, that's why they can also do stuff. A database does stuff as well. But they have some state that is important to understand. And we have to know for each of our components, well, is it really focused around doing stuff, or is it got some state that we care about? Because solving the resiliency for them is very, very different. If it's remembering something, if it has state we care about, it's generally a more complex solution to add resiliency to it. It's not saying we can't, absolutely we do, but I need to understand that about my environment. So what can we do to protect against infrastructure type failures? So I'm stressing infrastructure here. So some failure in the compute, the storage, the network, a building fails. If it's a misconfiguration, if I introduce a bug, then these things may not help. Now, the most basic building block for resiliency is to have another one. I can just think about, well, I'll have a copy of it somewhere. So if I think of, let's come over here. Imagine I have my element. So I have some unit of something. And the most obvious thing I can do to add some level of protection on this is I can just have a copy. So I can just have another one over here. And I'll copy that thing. Now, if it's state, then just having the state somewhere else may not be totally useful. I'm going to need something that's actually going to be able to use it. But copying the state is one of those first building blocks we have to do. Now, and there are many factors. When I think about just copying state, it's not that easy. because there's elements of, well, how big a distance do I have between these? Because the bigger the distance, the longer the time it takes to actually copy the changes over. And then it can impact, well, what is my tolerance for maybe losing a little bit of that data? So I have to understand those things as part of my planning. So copying something is kind of the most fundamental thing I can do to say, oh, well, that's a way to solve if something fails. If I have a copy of it, then something can happen to the original. I can also just have it exist running somewhere else. Now that's really useful if it's stateless. So consider the scenario here that most applications are not just a big process anymore. Most architectures have moved beyond just having this monolithic single big bit of code in one process. And instead I have the ideas of multiple different tiers. And as much as possible, when I start designing these things, what I actually do is I might have a 3-tiered architecture. So maybe there's some kind of compute going on here. Maybe there's some initial entry point going on here. And these all kind of talk to each other. But there's no state in any of these elements. The only place I have state is maybe in this bottom database type layer. It could be microservices. So I have different instances performing different types of functions, and a failure may just impact one of those things. And so the easiest thing I can do here is just have many copies of it, and there isn't anything I have to copy between them, because in these, there is no state. So as long as I architect my application accordingly, this is fairly easy. I have multiple instances, they talk to the next tier down, and then sure, there's state somewhere, but by only having the state in a particular point of my architecture, then I only have one place where I really have to focus on this. So in our picture of adding in kind of the resiliency, well, right, I would just have maybe copies of the stateless things over here as well. Maybe I'm running active. Maybe it's an active passive. Maybe I just create these when I need them. And it's only the stateful bit I actually have to have going and copying on. But I have different options around that. When we think of these multiple instances where I don't have any state, I can have these instances spread over different things. Like maybe these are in different data centers. Maybe these are in a different region, hundreds of miles apart. I get a lot of flexibility when I don't have to worry about this state thing and time things take. Now, again, remember, it probably is talking at some level to something that has state. And there's additional complexities around where we have the state. And we're going to spend a lot more time on that later on. But this idea of just being able to copy it somewhere, well, that's a really big thing. Additionally, I can have previous point in time copies. Now, this is when I'm now thinking about some kind of corruption level thing. Because look at what we drew before. If I just copy where I have state, if I have a logical corruption, not some physical thing fail, the data has been incorrectly changed, it's been encrypted by some bad actor. If I'm just replicating in near real time, if there's some bad bit of thing, some logical corruption here, well, that copy will just replicate the change over to here. So it's not going to give me a good resilience to logical type corruptions. So what I also need for stateful things is being able to actually go to some previous point in time. So what we think about here is we might have the idea of, well, snapshots is one component. So a snapshot, this is me trying to draw a camera, by the way, not very good camera, but a snapshot would be a point in time. So typically they store the delta. So it's only storing the changes since the last one was made. The initial one might be a full copy. But I might have this point in time snapshot. I might also take this and copy it to a completely different place. So I have some sort of backup vault. And that's also really useful for a prolonged storage capability. So I might have a snapshot that's really kind of local. That wouldn't give me resilience from a hardware type failure. But if there was maybe some logical corruption, I could roll back to a previous point in time. A backup would be on a completely different set of infrastructure. So then I could go and restore it somewhere completely different. And also it would be architected to maybe have that weeks old of retention, months old of retention, whatever I want. And when I think of backups, typically a backup would be stored some very great distance away. I remember when I was a VAX VMS systems administrator, we would have a company would come and drop off the backup tape each day, and then we would go and ship it, and they would go and store it at an offsite location. We would do a weekly backup, which had a longer rotation strategy. So there's all these different things you can do. But the point is here, I want to be able to roll back to a certain point in time, which replication doesn't satisfy, because it's just going to replicate those things as quick as it can. Realize also when I'm thinking about these types of capability, also the configuration might be important. Realize there might be images that I use to go and create a container or create a virtual machine or is some workload. So don't forget there's also elements that I'm going to have around some kind of configuration. Maybe it's images. Especially if I want to go and recreate in failure scenarios, I have to have some way of actually doing that. It's super common for things like configuration and images to actually use a repository of some kind. So I might actually have some kind of repo for configuration. And the nice thing about repos is they have this idea of like a version control. So I could go and store this, but I could also have versions. So rather than it just being a copy, once again, I would have those point-in-time views. So a repository with version control, say, hey, the config I'm using for this is what it was a week ago. Well, this was the time before that, before I made these various changes. For images, we typically use some kind of registry. And once again, you'd want to look at, well, what capabilities does this have around replication and things like that? But there's different solutions for the different types of artifact we may have. So, hey, if it's stateful, I'm probably going to do some kind of replication. If it's stateless, maybe I can just have copies of it. Those get created from some config and based on some image. So I want those stored in a resilient way as well. And that kind of is the sum of our complete architecture. So the whole point here is we have different solutions for different capabilities. And often you're going to have both. Very rarely is it, do I want replication or do I want a backup? Pretty much for everything, you're always going to want both. Now, I may not care about backups for those stateless things, because remember those stateless things, who cares about that? So it's not really doing anything I particularly care about. But I would still want a point-in-time view of their configuration, of their images. So while I may not have to back up the state of them, I still want to be able to back up, hey, what makes them up? How would I recreate them? And make sure you have good monitoring. Having a good benchmark of the typical resource usage, of how it should be behaving, that helps us be able to spot any kind of anomaly, because I can compare the current to what is that historical benchmark, and it makes it a lot simpler to go and see if something's going wrong. Like if suddenly I saw the memory was spiking, well, that would maybe indicate there's a memory leak of some kind. If I saw the disk space, maybe the logs, there's something going wrong there. I need to go and clean them up, or it might fill up the disk and crash the system. So I always want good observability, because the better insight I get into the system, that will actually help me improve the system. DevOps is a whole focus just on observability. So overall, don't forget about that ability to actually monitor and see what is going on in our environment. So understanding our replication requirements. So I want to talk about, well, what are the different elements of the solution that I have to understand when I think about replication? Replicating the data, that state, means I have to understand some of the key requirements that make it up. And one of the biggest ones I'm going to have to understand is, well, what is the distance between where those copies of the data are actually going to exist? Because the bigger the distance, the bigger the delay. Light is not instant, and light in fiber is even slower. So people think, oh no, it doesn't matter how far apart things are. I've had the weirdest conversations. people don't, I think, understand the difference. Like if I'm in a location, right? If I'm in a location here, and this is talking to this, I might have a millisecond of latency for this part. My relational database, my operations, they handle a millisecond easy. If I'm suddenly over here and I was talking to this, that might be a 70 millisecond latency. That makes a huge difference to the performance of your application, and it would cripple most applications if they suddenly had a 70 times increase in the latency to perform any operation. So it's really important to understand what are the distances between these things. What is the lag, the latency tolerance of the applications before I can really architect the right solution. So when we think about these things, we think about recovery time objective. So recovery time objective is how long do I have to get up and running in the other location if there is a disaster. So, hey, I lose my primary site. My recovery time objective could be 1 hour. So I can be down for 1 hour. Remember, this is a true disaster. People always say, I can't be down for an hour. This is not, a small component had a failure. This is a true disaster. This is an exceptional circumstance. And so it's going to be some magnitude of time. Now, for really mission critical systems, maybe that isn't an option. And I can only be down for 30 seconds. In those architectures, you're not doing an active passive. You're not just sitting here, in a disaster, I'll fail over to this one and I'll start these things up. When I'm talking about very, very low recovery time objectives, you're active. I mean, they're just running all of the time. And if it was a relational database, you do kind of interesting things where, for example, most interactions with a relational database are actually read operations. So these would all be active. They're all doing stuff. And maybe this would read from its local replica, but it would go and write to the primary over here. It would hit the latency, it would accept it for the write operations. But there are things I can do. We'll talk about other architectures later on where, well, maybe the database can be active. I don't need relational. There's things like NoSQL, and they give you different flexibility for consistency where I don't need that acid promise of a relational database where it's absolute guaranteed consistency and it will roll back all the transactions. Maybe I have some flexibility there. But I have to understand what is my true, realistic recovery time objective in a real disaster. I have to understand what is my recovery point objective. Again, how much data can we lose in an event? And once again, people may say, I can't lose any data. And then you say, okay, but if you can't lose any data, it's going to cost you $1 million. And they're like, well, okay, maybe I can lose a little bit of data. You have to balance those things. Realize that as you start shrinking things like recovery point objective, the cost can go up magnitudes because it gets way, way harder. Again, look at this picture. If this is copying things as quick as it can, but it's not real time, then in a true disaster, this just disappeared, we'll realize this would be missing the last few transactions. You'd have lost a little bit of data. So maybe my recovery point objective is I can lose 5 minutes. In a true unplanned. Remember, planned, I wouldn't lose any data. Planned, it would cleanly send the data over, then shut down, which is why you always want to try and do a planned DR failover and not wait for it to disappear. But if my recovery point objective is no, even in an unplanned, I can't lose anything, well, then we have to start architecting different ways of doing things. Is this now a synchronous replication? Is there maybe some way that if there's a system feeding into this, you could ask it to replay the operations? But you have to start looking at other things, and it gets way, way more complicated. So again, you have to have realistic metrics for what would I actually accept. And then you have the service level agreement. And the service level agreement is your uptime. What is the guarantee of you being available so the clients can go and interact and send you operations? It might be, you might hear 4 nines. So 99.99% of the time you'll be up. And this is generally something that is financially backed. And so there'll be a penalty if you don't meet that. And like 4 nines is pretty Typical, I think that's like 5 minutes of downtime a month. Again, people might say, no, I have to be 100% available. I don't think that exists. I don't think you can do that realistically. Now, you could have 100% SLA, but remember, that's just financially backed. It just means someone will have to give you some credit. But realistically, I don't know if there's many things that are 100%. It might be 5 nines, maybe it's 6 nines. That gets very, very difficult, as we'll see later on when we talk about SLAs. But you have to have some realistic number that you're willing to pay for. Because once again, the more nines I want, the way more expensive it gets because my architecture gets more complex. I tend to have more components there. I have different types of replication and synchronization and caching and other stuff going on. So then what can I do against those human things? This is not a motivational speech for artificial intelligence to try and overthrow us, I promise. But a huge amounts of problems are actually caused by the humans. Normally the human is like, oh, I'm going to go and make some change. So firstly, humans should not be touching production. Now, there might be break glass situations where something's already on fire and a human has to go and connect to the system to maybe try and do some troubleshooting. But I mean, remember, first do no harm. I don't want people just start wandering around in production. In any normal scenario, I do not want humans touching production. Humans should not be making changes in production. What I want is to have tooling to do this. Now, I might have orchestration tools, automation tools. Now, a caveat here, though. Automation is fantastic. Scripts are fantastic. I've written scripts before. I know people use them a lot. And with one line, I can do these fantastic numbers of operations on my entire server environment. So listen to that statement again. With one command, I can do fantastic things across all of the servers in my environment, thousands of servers. Yep, I can do fantastic things, but I'm also amplifying my ability to cause harm at a massive scale. If I have an automation that lets a human enter a command and now I can update massive amounts of servers, if they do it wrong, now I've suddenly taken down huge numbers of servers. I know before, was not me, honest, someone targeted the wrong group of servers. So instead of applying a change to the small test batch, they applied it to production. And it had a bug in it. So instead of testing it in this small batch, it bugged out, I think it was thousands of servers. So what I should have here is I have to human-proof my tools. Maybe it should detect, hey, look, do you realize you're running it against this many servers? Or this is production. You can't do this. You have to have a second authorization to do these things. So when we often see these ideas that it was a human error, I don't really agree with that most of the time. It was a failure of the system to not have proper checks in place to avoid human accidents. We are human. We are going to make mistakes. So what you really should have is the stoppage for the ability to humans to make mistakes like that. There should be a process in place so they cannot do that. So what we'd like to do is automated deployments that are triggered via some kind of version control or job submission that goes and validates those particular things. So we drew this idea here of this repo. And often what we're actually talking about here is it's some version control. So it's some kind of Git library. So it's a repository. And what I actually want in this scenario is I want my human being, they're on their machine. Now this should be for anything. This could be maybe they're a developer and they're writing some code. It could be a change to configuration. So I'm doing it as infrastructure as code. It could be some configuration to the environment. It could be a database schema change. Whatever that is, what they should be doing when they make that change is they're going to commit it to the version control system. Now, at that point, I can have all number of wonderful different things to go and have someone else validate it. I can have automated things. I can have lots of things going on. And then what would happen here is when I do this commit, we have the ability to have something called pipelines. So I could now think about, I have some pipeline. when I have a commit to maybe my main branch or there's some testing things I'm doing, this will trigger the pipeline to run some set of actions I want to perform. And once again, before it even gets committed, or I can put in a pull request like my main branch, which has to be reviewed by someone else, but before it ever touches production, we're going to have a whole bunch of different things happen. So there would absolutely be checks performed, looking for bugs and maybe viruses. Maybe I'm using an out-of-date library. I might have some kind of build operation. And then that would go and get deployed to a test environment. And then there'll be a gate to stop it going any further. And then once it passes that gate, well, then it may go and deploy to a user acceptance test environment. And there'll be another gate before it can go any further. And then after maybe a certain amount of time, once it's looked at the ticketing system and make sure there wasn't more than 10 bugs raised or whatever that is, then it might go and deploy it into a production environment. And there's all these different things and checks and capabilities. But the point here is there is no human deploying to production. In all of these cases as well, I can have automated testing going on. I can introduce different types of failure. All of those things will be happening. So some poor human who's having a bad day and is a bit tired doesn't accidentally just go and deploy a bunch of stuff to prod and break the world. So you need to protect your systems from us carbon-based things because we are human and we make mistakes. And again, monitoring. For all of these things, for the humans as well, I want to monitor to see if something's behaving differently. Is the resource use different? Am I getting different numbers of errors? As part of our testing, I shouldn't just be looking at individual components. Like I shouldn't just look, is the VM healthy? Is the app healthy? Is the database healthy? Because it might be the problem is some communication between them. So we want synthetic transactions. Synthetic transactions are fake transactions that we run that go through the whole system. So a synthetic transaction would come in through the entry point, it would go through the middle tier, it would do some operation, and it would expect a certain response. And we create those, and we would have our test system submit those and check we get the right response in a decent amount of time. So those are critical to have as part of your solution, because absolutely, I don't want to just rely on the health of any individual component, because they're all healthy, but something is really broken between their communication. So while every individual element looks good, the reality is the actual workload isn't working anymore because something is broken within their interaction. So it's really important you have quality types of tests going on that is testing the complete end-to-end flow of what you're doing. Which leads us to safe deployment practices. Now, I did a whole separate video on this. There have been some very public issues, not actually Microsoft, because a certain antivirus company pushed out change that wasn't tested correctly, and things happen. But the problem here is they just deployed it to everyone all at once, which you cannot do. And this was a kernel mode driver element where it was used by kernel mode, which then meant it just crashed any Windows machine that had this. So we have to do safe deployment practices. And if you remember nothing else from the rest of this course, remember this. When we make any change, we don't make the change everywhere all at once. What we want to do is gradually roll out the change through our environment to progressively larger segments of more importance as we gain confidence in the quality of whatever that change is. So it's a progressive exposure to whatever the thing is we are changing. So we would start with a very small, least important thing, and then we start building up to more important things as we gain confidence that, hey, this is not going to destroy my world. And this does apply to any change. If I'm changing the type of a VM resource, if I'm changing its size, if I'm changing a database SKU, if I'm adding a new element to the architecture, if I'm upgrading or updating the operating system, a runtime, an app, if I'm changing a Kubernetes version of AKS, if I'm updating a config, if I'm updating an anti-malware. If it's a change, we do not do it everywhere at once. I mean, that's fundamentally the point. Nothing happens everywhere at once. And deployment patterns are really our friend when we want to roll out any type of change. And these are all about, before we hit some critical population, we would find the problem, or at least we have some ability to roll back if there is an issue. Now, for your very early testing, a lot of the times you'll actually probably have some dedicated test machines. And then you can only test certain use cases though. So then you might have, well, from each of your key business units, you would have maybe hero users that are the early adopters that would help test those. Maybe they're more IT savvy. They would help you with those things. And those pipelines we drew, they should absolutely be facilitating this. So realize I drew this just as, oh, it's deploying to production. But the reality is it probably wouldn't be that simple. I would want these to do various types of things to help me. And there are a lot of different, I'm not going to go through them all, but you have the idea of something called canary. And this is from the mining days. So a canary would be a very small group. So your change would initially go to this canary group. And then, assuming they don't all explode into flames, then you might go and roll it out to everyone else. But something else is I use rings of deployment. And canary could still be the first ring, but then what I'm doing is I start rolling it out to increasingly bigger elements of the population that also are getting more important. So my initial machines will be very unimportant test machines, maybe dev machines, maybe some testing elements. Now, the key point, though, is realize I still have to be hitting the scenarios. It's no good just doing all of my testing on unimportant machines, then all of production is in the last ring. Because maybe it's only production that does a certain type of operation. Maybe my testing is not that comprehensive. Maybe it's only production that runs at the scale, and so the problem only manifests when it hits a certain type of actual performance it has to run at. So it's no good saving prod for the end. I would still need the ability to either have very high quality testing systems that do replicate all of the functional elements that production does, that does estimate a proportional amount of scale that it does, so I would find the problem, or I have to scatter them. Maybe it's a certain region or a certain availability zone, which things we're going to talk about, within those places. But I cannot just leave production to the end. I have to make sure I've tested that set of capabilities. And there are other things like blue-green. I guess I should use blue and green unless I'm being really lazy. So blue-green, the idea is I have two environments. So I could think about I have a blue and a green. And what I would have here is I could think about, well, production is currently running over there. So what I would have is there would be some load balancing capability. So this would be the endpoint that the clients, could be other systems using an API, it could actually be client machines, whatever that is. So it's normally pointing to blue. So blue is running the production code. Well, now I have my sparkly new code. So I would deploy that to green. So this is the V2. So this is a completely different set of infrastructure. What happens now is I can actually run some tests in here. I can warm up the code. And then once I'm satisfied it's ready, there's actually different things I could do. I could do things now like, well, I'll repoint the load balancer so it now just points over to green. Or I could move 10% over to green and leave them. Again, I can start to build that confidence in those various things I'm doing. I can have a feature flag. I can have A/B testing where I split different groups. There's amazing things I can do here. But the nice thing about this is if I then discover a problem, this is still here running the V1. So I could always go, oh, okay, I need to fail back. And I can fail back really quickly because I can just point back to this. Now, the challenge with this approach, and you look at this, is like, well, that's a lot of spare infrastructure. In the cloud, remember, I can create it as I need it. So if I only do releases maybe once a week, well, maybe green doesn't exist until I have a new version. I go and create green, populate the new code, do the warm-up, do the tests, switch over. Once I'm confident it's good, I don't need to fail back, I delete blue. Then in a week's time, I create blue. I put the V3 in, etc., etc. You get the idea. And so these are all ways that's designed so I don't hit just everyone all at once, and I get that ability to roll things out over time. So these are really useful things that you should be using for everything. I know I keep saying that, but this is for everything. Another consideration here is do consider your ability to remediate if there is a problem. So don't roll out the change initially on a system that's hundreds of miles away with no one at that office. How am I going to fix the thing? Don't deploy on Friday. Again, do you want to be working all the weekend and maybe no one discovers it over the weekend, so Monday is just this huge explosion? So think carefully about all of those different considerations when I'm planning out how I want to do my various things. Okay, so what are we actually protecting against? So I want to summarize all of the things we've just talked about. So hardware failures. Okay, for hardware failures and really software failures, our solution is we have copies. If it's got a state, we have a copy of that. If it's stateless, it's not a big deal. I have to make sure the config, the infrastructure as code, the image is there available. But then either I just have it running, not doing anything, or active, or I create it if there's a failover. If it has state, then I have to copy it. I have to have some kind of replication going on. If it's a corruption, replication doesn't help me. I need to have snapshots, which are typically in place with the primary data, or backups. Because remember, replication would just replicate whatever that corruption was. If it's an attack, well, now I have to think about some kind of an isolated set of capability. Now, we always want to make sure people have minimum permissions as possible, but my backup is no good now if my backup is in the same location or the same permission structure as my primary copy of the data. Because if there's an attacker, they're not just going to try and corrupt your database or your file share. They're going to go and look for backups and corrupt those as well. So I would want an isolated from a blast radius, so a different user credential has permissions to my backups to help give me protection from that. And we'll talk about that later on in this module when we talk about multi-user authorization. That is a capability we have in Azure Backup. Because most likely, if you're being attacked, a user account has been compromised. And so if the same user account has permissions on all your backups, well, you're not in a great position because they can go and compromise those as well. If it's like a denial of service, well, there are protections such as there's a distributed denial of service protection capability. We have intelligent firewalls that can sit in front of web application firewall that's regional or Azure front door. So we have things to help give us protection from these types of attacks. For regulatory requirements, depending on what they are, maybe it's just we have to keep backups for a certain amount of time, just make sure we understand those and adhere to them. And then for those human things, we just have to have good processes. That's really what it boils down to. For the human elements, you cannot trust that a human is not going to make a mistake. You're going to be in a world of hurt. Humans will make mistakes. So my systems have to either have limits on it, checks on them, I commit and someone else validates, and I have tools to go and automatically check things. With the new AI capabilities, what's nice is I can actually use that to do like a checker pattern to look at, well, what is this change? And maybe summarize, well, this is what the impact's going to be. There are some nice things I can do with this. Avoid pets. This is not having a go at my dogs, Ollie and Eddie. Sorry about this. My point here is things will go wrong. Servers fail, disks fail, OS instances get corrupted, there's some accident. And what I really want to avoid is having these highly specific snowflakes that are very, very special and that I have to care and feed. And if they break, I have to fix them. I have to spend massive amount of times trawling through to understand, well, what is it doing to bring it back to life, to make it be healthy again? I do not want that. From a resiliency perspective, we like the idea of cattle. And what I mean by that is they're not unique special snowflakes. They are replaceable. Everything I have, as much as possible, should be replaceable. I can recreate it at any time should I need to. So I would not spend the time caring and feeding it, bringing it back. I would just delete it and create a new one in its place. So the whole point here is, I talked before about that version control things. I want version control, infrastructure as code, all of the configuration using declarative technologies so I can just recreate it. So that would be my infrastructure, that would be my workload configuration, my app configuration, my Kubernetes manifest, my OS, everything. I should be able to just, via my version control, via those pipelines, if something goes wrong, I rerun it and it will recreate the resource, reapply the configuration. In a disaster scenario, consider maybe my recovery time objective is really long and it's not that critical. But in a disaster then, I don't even have to have this, apart from the stateful bit. I could just rerun my pipeline. It would recreate the entire environment in my DR location. So that's a really nice capability. So I want this. If today your production is you following this guide and creating stuff, I would stop. I would go back and think, how can I automate this? How can I use pipelines and version control and change how I'm doing that? And I don't want state everywhere. Remember, state is the complicated bit. Because state, I have to think about, well, how do I get the state copied around and how do I manage that? There's a lot of complexity when I have state. So instead, try and get your state into a particular place. I can then rally my efforts to handle the state replication and keeping that healthy. It also minimizes the number of components, maybe an active passive I have to have running in my DR location. I don't want it spread over everywhere. I do not want every element to have to be replicated. I really want one bit to be replicated. Everything else is stateless, and I can just recreate it as I need to. That's the ideal. I need to understand my services. I need to understand which ones are important, which ones need to be protected. So understanding the systems that are key to your business is critical. Now, you probably do not know. And by you, I'm assuming you're watching this course and you're more of an infrastructure operations person. You probably do not know which systems in your company are the must-haves. They're the ones that enable your company to do business, to sell whatever product maybe your company sells, versus the ones that are really not that important. Your time entry system, I don't care if that's down in a true disaster. So you're probably going to have to talk to your business groups. Your business units will know what are the systems that actually enable them to do business. But realize they may not fully understand the dependencies on what other things actually talk to. So they can probably identify, hey, we use this system. You would then need to understand the makeup of those systems. You would have to then go and understand, well, what are the actual elements that I would care about? So once again, as we kind of talked about, so let's go over here. So you're going to have some application, but realize your application is probably going to have, okay, so there's some web tier that requests come through and talk to. And then that goes and talks to some app logic tier. So maybe this is running on AKS. Maybe this is AKS as well. Maybe there's some Azure Functions or Logic Apps or whatever it is. And then this goes and talks to my database. Now realize a more complicated system this might be this huge mesh of different connections. You're just going to have to understand that. But you need to look at each of those and say, well, okay, where is their state? And you'll end up with kind of an idea of saying, okay, well, there's no state here. Oh, but there's state here. So I need to understand those different capabilities. I need to understand where are the bits that I really need to know about. And they may not understand that. Now also realize, even if there's no state, they still may cache things. There could be other systems. There could be like a Redis cache that caches things that gives you a huge performance boost. Now realize if I failed over, if the cache isn't populated, I'm going to take a performance hit as those cache starts repopulating as it does the operations. And so that would have to understand, is that acceptable or not? Or do I need some capability to try and mirror cache state so that I don't drop performance in the event of some kind of failure? But additionally, what are they dependent on? Because sure, I might just say, well, these are the elements of my architecture, but I bet they rely on other things as well. So let's just say this web tier, for example. They are probably dependent on some web application firewall that sits in front of it. And that's in front of a load balancer, which then goes and talks to that. So they're dependent on this being functional. This database, well, they like to use a customer managed key. Well, that customer managed key is sitting in a key vault. So I'm relying on key vault as well. And actually, these things all have to, especially the app logic to the database, it has to have permissions to the database. So they all have an identity. And so there's Entra. My Entra instance, these are all using this for their identity. All of these things. So we'll have a reliance on Entra as well. And the list goes on and on. But the point is, make sure you really know what are your dependencies. And some things you have no control over whatsoever. Like from an architecture perspective, if I'm relying on Key Vault, and I've done a whole video on this, so I don't want to go into detail here, but yes, Key Vaults will replicate to the paired region if it has a paired region, but I would recommend against that. I would recommend against having these global secrets. From a best practice and to limit impact if there's a problem, I would just have different secrets per region, per cell, per stamp of your solution. Entra, you have no ability to add resilience to Entra. It is a global service, but there are things you can do. Use managed identities. Managed identities give you a nice long-lived 24-hour token. So if Entra was down for a long time, it proactively refreshes the token at 12 hours. So I've always got 12 hours of token lifetime left. It uses a regional secure token service. It has backup auth. So basically, use the capabilities that the platform exposes to you to help you be more resilient if there were potential failures. So I always want to use managed identity, for example, because that gives me the most robust Entra capability. Now, if you're not sure of the person who developed this, they gave up on IT, they're now baking bread, whatever, there are solutions to help you. So Azure Migrate has a discovery and assessment, and it can help work out which apps are talking to other apps. It looks at the network traffic, the ports that are being used, and obviously there are well-known ports that mean, well, this is SQL, etc. So it can help. Azure Monitor has a service map that has VM insights based on network connections. App Insights has an application map based on the APIs. So instead of using the network traffic, it's looking at what APIs are being called between the app. So there are things to help you understand what are my actual dependencies within the application, but you have to know that. So make sure you have a good understanding of which apps are important, the makeup of the app, what it depends upon, and also make sure you're thinking about, well, how do I use the app? It's no good having this ironclad super process, we're in a disaster, I can make the app available and it's resilient, and no one can get to the thing because I forgot about, well, they use this jump box and I forgot to make the jump box resilient. Or they VPN in. Oh, the VPN's only on in this location. So make sure you're thinking about how is it consumed, right? Whatever that is, make sure that is as resilient, it's matching the requirements, because just having it available and resilient is completely useless if no one can actually get to the thing. So just a nice to know. Okay. Understand your requirements for the availability and architect accordingly. So this again is going back to what are those core constructs? And then what is my architecture enabling? And really what I'm focused on here is most of the Azure services have a service level agreement. So this links to a big document, and the big document will go through for each type of resource. What is the SLA? Remember, SLA is financially backed. It is, hey, if you don't get this level of availability for this particular type of resource, there is a financially backed refund, essentially. And different services have different SLAs. For a VM, for example, a single instance, the SLA varies depending on the type of disks. The better the disk you use, the better the SLA you get. And depending on the criticality of your service, remember, you're going to have different requirements. Now, the cloud is not magic. The resource is not just always going to be there. A VM, where's the picture? It's not magic how this thing's, like an Azure VM is still running on a host, it's still running in a rack. They have fantastic resiliency features, but the host can fail, the rack can fail, the switches can fail, the power in a data center can fail. They have to perform maintenance. Some virtual machines, they can live migrate to another host, some they can't. So there's a VM preserving host update. It lets them, you don't have to shut down the guest. It pauses it in memory while they update the kernel, and then it unfreezes it, but it'll still be unavailable for some tens of seconds time. So you realize it's not just always there. Things can happen, which is why there are SLAs and they're not all 100%. None of them are 100%. So there's a certain promise backed by money of the resilience of any particular capability that exists in Azure. And so as I architect my solution, I have to look at, well, okay, what is the individual component? How do I get this SLA number close to what I actually need? Now, when I look at these SLAs, it's going to be a price impact. I mean, just very realistically. And I mentioned it earlier that they say, I need 5 nines or I need 6 nines. It generally is a massive magnitude of cost increase to increase those SLAs. And we'll look at an example in a second, but it's not a simple thing. Going from 3 nines or 99.95 to 9999 may cost $100,000 extra over the year. Whereas those few minutes difference might only cost your company $1,000. It's likely not worth it in those circumstances. So although people may say, I have to never be down, it's completely unrealistic. It's very hard to achieve anything like 100% SLA anywhere. Anyone who tells you that, they might be financially backing it, but they'll be paying out some money at some point. But 5 nines, like mission critical systems, absolutely can happen. You do have to consider, though, it may not be the financial impact. So maybe it's only $1,000 of lost sales, but my reputation could be damaged. So realize reputation may be more important than that few minutes of downtime because it'd be very public, it's very embarrassing. There may be regulatory implications. So it's not always just the dollar. Understand the impact for your business, which again will be a business unit conversation. Hey, look, what is the actual impact to us if we are down? And then I need to architect my application accordingly. So I have to architect it to meet what is the requirement. And your overall SLA it's where we get something called a composite SLA. Your composite SLA depends on how the different resources are architected and if it's an and relationship or an or relationship, which is a little bit strange. But look at my picture here for a second, this one. So in this instance, these are or. Like, they don't all have to be available. I just need one of them to be available, and the balancer would send it to the active one. So these have an or relationship between them. So having more instances makes it more resilient, more reliable. It would increase the SLA of that tier. But this tier requires this tier. So this is now an and relationship, because both of these have to be available for it to function. And it requires this. And, all right, we're back. But realize I'm also have a dependency on key vault. I have a dependency on the load balancer. I have a dependency on Entra. So all of those things, realize, are absolutely part of my overall SLA. So to give you an example, super simple example, and not even very good, but I'm going to think about, I have a certain resource. And this resource has a terrible SLA. It's 99%. So what does that mean? So let's take this out of 1. So what this SLA means is, let's do good and bad. So it should be available 0.99 out of 1 of the time. And it won't be available 0.01 of the time. Okay, easy enough. So now imagine I have 2 of them. But this is a different tier. Imagine this is the web tier and this is the middle tier. So now if I need both of them, and let's say this other one also has a 99% SLA. So once again, this has a 0.99 chance of being there, and then a 0.1 chance of not being there. So that same challenge with how good and available, oops, didn't mean that, sorry, how available it's going to be. But I need both of them. So now I'm in the scenario, it's an and. So if I think about my availability, it's 0.99 times 0.99. So my overall SLA becomes 0.98. So 98%. So my overall SLA has dropped, which makes total sense. If I need 2 things to be there for me to function, if either one of them is down, my system doesn't work anymore. So that actually makes sense, and it gets worse. So the more dependencies I have on things, my overall SLA gets worse. But now imagine for this tier, I actually add a second instance. So now we add a second instance, which is still 99%, which means it has a 0.99% chance of working and a 0.01 of not working. But I only need one of them to be there to function. So now the relationship is an or relationship. So now I care about the probability of them both not being available. So now that was about them being available. This is now about it not being available. Well, the chance of them both not being available is you times the not together. Also now I get 0.0001. So if that's the chance of it not being available, like both of them not being available at the same time, it's very small. So the chance of them actually being available would be 1 minus 0.0001, which would be 0.9999, or a 4 nines SLA. Which again would make sense, right? Because if I only need one of them, what are the chances of both of them being down at the same time? And so that the point here is you can improve your overall SLA by adding alternate paths. I can add resiliency. Now realize you're going to have a combination of all these things. So the tiers are going to be an and relationship. Within the tier, I can make them more resilient. But remember things like intra. If that's required by all of them, I can never exceed the SLA of intra. Now, I've got detailed videos on all of these different components. But the point here is don't have single points of failure. Avoid single instances of anything. Try and have as much redundancy as you can to meet your SLA. Obviously, this costs money. The more resiliency I need, the more components I'm adding, it makes it more complex and it's going to cost me more money. Don't make it just super complex for the sake of it. What is the SLA I need for my business? And then architect to that. Now, I'm talking about really the components in Azure here. Understand there's maybe another service talking to this. Remember, there's load balancers in front of this that has SLAs as well. There might be stuff I can do on the client side to add resilience. So I care about my all-up workload solution, and there could be a client over here. My client I could add resiliency in. Maybe it can cache the last address it spoke to so it can survive the load balancer being down. I can cache a DNS name, whatever that is. I can add things like circuit breaker, so if it has so many failures, it stops, doesn't just keep hammering it, which will make the problem even worse. I have bulkhead patterns, so a failure doesn't propagate down to other components. So there's a whole lot I can do to architect a good solution. But the point is, I have to understand what is my actual requirement, and then I have to architect to that requirement. It's not just magically going to appear, and just because it's running in the cloud, I don't have to worry about anything. That's absolutely not the case. I am architecting my solution. I have these building blocks. The building blocks have their own SLAs. I need to plan accordingly. Test, test, test. Most of the things we're going to talk about, they actually start with the testing. So, and there's many different types of testing. Yes, I test the application testing. There's load testing. There's deployment process testing, failover testing, restore testing, security testing. And the list goes on and on. Unit testing, integration testing, smoke test. I mean, you need to do very thorough testing. Realize though, whatever testing you do is never going to be as creative as the average user. There's a joke I like. A software tester walks into a bar. The software tester orders a beer, 2 beers, 0 beers, 9,999,999 beers, a lizard in a beer glass, minus 1 beer, QWERTY beers. Testing complete. A real customer walks into the bar and asks where the bathroom is, and the bar goes up in flames. You're never going to be as creative as actual real-world usage scenarios. So just you try and be as powerful and as broad as you can in your testing. Your DevOps pipelines, remember, as much as possible, should be having automated testing. Like there's Azure testing capabilities. There's other things I can do to inject failures, which we're going to talk about. But as much as you can, try and be imaginative. Don't just in your testing, test the scenarios. You need to send junk data, send illegal data, overload an instance, have a certificate be out of date. Like I need to test with good and bad data. So the Azure load testing is built on Apache JMeter. It can automate creating those scripts. I need to have all of those different scenarios as part of it. Because if all I do is test what I expect, yeah, I need to be able to handle the where is the bathroom scenario. So make sure I have that. Yes, you need to understand what the real traffic is. Make sure you understand what is the load of the traffic coming in. Cloud helps with that. If I do get these bursts of traffic or I get these variances, if I architect correctly and I can auto scale, then hey, that does help. It takes time to auto scale though. It's not instant. But if I have my maybe threshold set accordingly, there's things I can do to that. What happens though if a user session hangs and locks some record? What happens? What are your timeout capabilities? So it's all things that happen where what would actually happen with the system if these weird scenarios happened. Make sure you are testing your failover. Make sure you're testing your backup restore. Again, I talk about the backup tapes in my early career. I remember there was one bank that had updated the backup system, but they never updated the backup system at the DR site. So they actually had a disaster and they went to restore the tape and it didn't fit in the tape drive. You get these digital square tape things. That's a huge failure, which is why, again, any change you make needs to be part of change control, which considers what is the DR impact. Security, you're shifting left with all of these different things. So just test, think of all these different capabilities. I'm just trying to reduce the chance of actual problems. Now realize problems are still going to happen, which is why we have this chaos engineering. When you test, as I mentioned, you are not as creative as a typical user. You're just not. There's always the first experience with reality. The users will find things you have never considered. Someone writes an application that talks to your API that they did a terrible job with. It sends absolute junk, or it hammers your endpoint nonstop. But you have to handle that. Like, you have to be able to do something around that. And so whatever you think you've done is not going to be good enough. So what chaos engineering is about introducing failures into the system. Especially on complex systems, it can help me find weak points, but it can also help me gain confidence because it will highlight things and I can fix things. So it will help you find issues. It will build that confidence. And Azure Chaos Studio helps do those things. So what's going to happen here is you create these experiments. And these experiments have different types of failure in them. And I could think about, there's things that it does with an agent. So it could use up all of the CPU in a VM. It could create a pod in Kubernetes that does some weird things. It could imagine Key Vault is not available. It could make all of the resources in availability zone unavailable. Now realize, this is not emulating the failure. It is actually making those things not available. It is actually using all the CPU in a virtual machine. It is actually adding latency between these things. It is actually killing processes. And so I probably want to start with this in my dev environments. And then, sure, I could introduce, as I gain the confidence, right? As we always gain that confidence, then I could start introducing failures as part of my pipelines as I roll through the environments, because I want to make sure it works in my production environments as well. But just make sure you consider those things. I would also encourage you, as part of planning the chaos engineering, is, and I don't mean it this way, take out people, not permanently, but they have to take 2 weeks off. Imagine 10% of my team are zombies for the day and can't be contacted. How does that go? That will help you identify if you have some snowflake, unique human being that without them, you can't function as a company, or you can't fail over, or you can't fix the problem. You do not want that. So it's important you understand those things. I remember I used to work in the banking industry, and we were required to take 2 weeks consecutive time off each year where we were not allowed to be contacted. Now, that wasn't so much about, I think, finding problems. It was about if we were doing something financially illegal, it will get discovered in those 2 weeks. So it was about that. But it was still, the point was, I want people to not be available so I can test, well, am I going to handle these things? Okay, so baskets, strange concept here. But we talked before about having copies of things, about replicas of things. Well, having copies of things or replicas of things would be pretty useless if they were running on the same physical construct. If they're running on the same node, if they're running on the same rack, if they're running in the same data center. I want to think about blast radius isolation. So when I think about my baskets, one basket is not very good. I don't want all of my resiliency things in the same basket. So maybe I have 2 baskets. So this could be separate racks. Maybe it's separate data centers, isolated power substations, isolated cooling, network, control planes, things like that. Then I probably also want baskets, huge physical distances, which again, resiliency there, because if there was a natural disaster that took out both the baskets, well, I don't want them to take out my sort of DR. So I have to think about having those distances between them. So what are these isolated boundaries of impact that we have available in Azure? So I want to talk about what are the Azure resiliency constructs. So these are the various isolation blast units we have. So a fault domain. This is the most basic structure. Azure is really made up of clusters, stamps, scale units of compute and storage. They're not clusters as we think about it in Windows Server. They're a scale unimaginable to that, but we consider them clusters. They have some commonality in their control planes, things like that. So Azure is made up of servers in racks. Well, a rack is a fault domain. So if I had this idea of a rack here, this would be a particular fault domain. There's some resiliency if they're in the same rack, if they're on different nodes. But if the rack had a failure, well, everything within that particular rack would fail. That is not a great thing. And so our first construct is something called an availability set. And when I have VMs in an availability set, I get this 99.95% service level agreement. And what's happening here is let's imagine we have 3 racks. Now these 3 racks, maybe this is fault domain 0, fault domain 1, fault domain 2. It's generally 3 fault domains is what you're going to see. That's what you're going to see in an availability set. Things like virtual machine scale sets, they let you set a fault domain count of 1, which will try and use as many as possible. But these are all really within the same cluster. So I'll consider them all within the same facility. So they're not going to give me resiliency against the entire data center going down. They're shared fabric controller, for example. And what I do with an availability set, I think of an availability set as some kind of anti-affinity. So if I create an availability set, so we call it availability set 1, it's going to basically span across 3 fault domains. And as I put resources into the availability set, it's going to spread them out as much as it can. So the first VM would go here, second one here, next one here. You get the idea. So it's trying to keep them spread over. So as long as I have more than 1 instance, if I have 1 instance in the availability set, it's useless. It's not getting me anything. So I would need to make sure I have at least 2, ideally 3, to maximize this. So now they're spread over these different racks. So my isolation and my blast radius is this entire rack could go down. My workload would still be running because they're on different racks. So that's a huge benefit that gives me. Additionally, I can, if I use managed disks, it can do an alignment. So for each fault domain, the managed disks that it's using would be on a separate fault domain for the storage. So I don't have resilience on the fault domain of the compute, but then they're going to the same storage for the disks. So if the storage had a problem, they'd all be down. So it adds a specific type of resilience there as well. The important point here, though, is this is dumb. It has no concept of the workload. So I cannot mix workloads in an availability set. What I mean by that is if I had domain controllers and IaaS web servers and database, if I put them all in one availability set, through sheer bad luck, the DCs may all end up on this rack. The SQL could all end up on this one. The IaaS could all end up on this one. I'm not getting the benefit. It's just kind of round robin, distributing the stuff. So what I need to do is create a separate availability set for every unique workload. So I would think, okay, I've got an availability set for my domain controllers. So I create that. So then my DCs would definitely get spread over the different racks. I would create another availability set for IaaS workload 1 because it has a set of IaaS servers, so then they would get distributed. Then I have a different IaaS app. I'm going to create that in a different IaaS availability set because, again, I want them spread over as much as possible. So it's a unique availability set for every set of unique workloads to ensure they all get that anti-affinity distributed over. There's also something called an update domain between 5 and 20 I can have. And that's when I'm rolling out changes to my app. So it only takes down maybe a 5th at a time or a 20th. I set that when I create it. It's also used for certain updates to the underlying fabric as well. So the key point here, though, fault domains give us resiliency from a rack level failure. I have to have a minimum of 2 instances. It's not magic. If I have 1 instance in an availability set, it can't spread it out over multiple racks. So make sure generally you want 3, but minimum 2. So you've got resilience from any one rack having a problem. So this is the key point here. And this was the original construct we had. And then they introduced availability zones. And availability zones has a 99.99%. Now, not every region has availability zones. If we look at documentation, it talks about the regions that have availability zone support, but it's quite a lot of them and they're adding them over time. Now, what exactly is an availability zone then? So remember, the whole point with the availability set, it was multiple racks within a specific facility. So within a specific cluster. If we kind of zoom out, so now I still have data centers. So now I'm drawing not the idea of a rack, but I'm drawing a specific data center. And there are these groups of data centers, multiple data centers, not just one. So I'm going to draw some groups of data centers. I'm drawing 3 for a reason you'll understand. So I've got these sets of data centers. And each of these sets of data centers is an availability zone. So this is one AZ, this is a different AZ, and this is yet another AZ. And the whole point here is when I think blast radius, obviously they're different physical facilities. Now there is no guarantee of distance between them. So that's a key point. There is no set distance between these sets of data centers. But what is isolated between them is they have isolated power. So generally you think different substations, independent cooling systems, independent network capabilities. So now there's a resilience from a lot of different things that this entire set of data centers could have an impact, and it wouldn't impact these other sets of data centers, providing I actually had my workload distributed over these. Now, your subscription will see 3 AZs per region, provided that region has availability zones. Now, that is a logical mapping. And what I mean by that is one subscription may see this as AZ1, this is AZ2, this is AZ3. A different subscription, this could be AZ1, this could be AZ2, and this could be AZ3. So it is not based on, hey, these physical buildings are AZ1, 2, 3. Every subscription sees them kind of muddled up, because otherwise AZ1 might get all of the use. So it's mixed up between them. But all of these AZs are within a specific region. And the promise here is there is a 2 millisecond latency round trip. So even though I'm spread over different physical data centers, the latency is still very low. I now have resiliency from an entire data center or power substation or cooling infrastructure or network. As long as I need a minimum of 2 instances, so they're spread over this, I would be resilient from that data center level failure or the different services that feed it. And this is obviously superior than availability sets. Availability set, well, I can survive a rack, or maybe 2 racks being unavailable. Here, my resiliency is I can survive entire data centers being unavailable or losing power or calling or networking. So generally, we're going to use this above availability sets if it is available to us. So that's really a key point there. And then our next construct is regions. Just using multiple regions. Now, at minimum, we want to use at least 2 regions, even if it's active, passive. And that's really going to depend on what my requirements are, what my capabilities are. But there are regions all throughout the world. Now, there are pairs of regions. That's going to show this. Most regions have a pair. So if we scroll down, these are showing all the pairs of regions. They're generally within the same geopolitical boundary. There's a few exceptions, but for regulatory reasons, they're generally in the same. And also generally, they're trying to replicate a big distance apart. So there's a big distance between them, because obviously what you don't want is I'm replicating certain things or resiliency that the same natural disaster could impact both of them. So there's a big distance between them. But honestly, this pairing is being de-emphasized. It was a huge deal initially when Azure was focused around those pairings. Things like geo-replicated storage, Azure Key Vault, if I need those replications, some of the backup things still uses the pairs. But I generally, these days, would recommend almost against using the paired regions. Imagine you had a problem on your primary region and you tried to fail over to your pair, everyone else is trying to fail over to that pair as well. There'll be a rush on the bank scenario. I would rather use many regions to give me more flexibility and not try and be failing over to the same place as everyone else. Like the Key Vault scenario I talked about, well, I'd rather actually have separate secrets anyway in the different deployments I have. Storage, I can do object level replication. There's pretty much solutions to all of the things. The staggered rollout by the paired regions is still semi-valid, but even there, it's generally AZ by AZ has that same construct of capabilities. So I would recommend, honestly, at this point, yes, you want at least 2 regions, but I did an entire video on not using the paired region. So I want another region, ideally regions. I would like to be using 3, 4, 5 regions. Why just use 2? As my architecture evolves, I can probably be active in all different places. That's just even better. The more instances I can have, the more regional flexibility I have, the better. But the key point I must have is I want distance. Because what I don't want to be is my DR region or whatever is in like 20 miles away. Then I might have the same natural disaster hit both of them. So I want that separation between them. And again, in this other region, I've probably got AZs as well. So there's probably a whole set of things. And I would use that as well. I think I just drew Mickey Mouse. I don't know what that's supposed to be. But you get, again, the same different sets of availability zones where I can. And I want that 100%. I absolutely need to focus on having more than one region. If I'm just using one region, that's a very bad thing. Azure has never had, touch wood at this point, a complete regional outage, but it could happen. Things happen. You need your solution now. How you use multiple regions is up to you. It depends on, remember that recovery time objective, recovery point objective. If I have 2 hours to be up and available, then I could probably just be passive over here. Or for the non-stateless thing, just create it at the time of failover. Providing you have regional flexibility though. Remember, if you're using the pair and in a true disaster, you're going to try and create all the resources over here along with everyone else, it's probably going to be a painful day. Whereas if you're using non-paired and I have flexibility and I have flexibility in SKUs, that's a better story for you. So I would always try and, hey, have flexibility in the regions, flexibility in the types of SKUs, like the VM types I can leverage. That's going to give you the best resiliency an ability to scale and create resources whenever you need to. But absolutely, you need to be thinking about multi-region. So I think AZs for high availability within the region. And then I always think using at least one other region for now that geo separation, diversity, and ability to survive some very large scale type incident at a particular point. So that's just a huge thing I have to think about. You may have heard another term, proximity placement group. This is not a resiliency function at all. It's almost the opposite of that. A proximity placement group is the idea that I have certain resources that need to be very close together. They need super, super low latency. And AZ doesn't actually guarantee proximity because, again, it could be multiple data centers, so it could still be fairly spread out. Proximity placement groups has certain guarantees about number of sort of network hops between the components. So it gives me a super low latency between those things. So a proximity placement group is about keeping things very close. It's really the opposite about trying to keep things separated to be isolated from any particular type of blast radiuses. So it's important to understand proximity placement group is not a resiliency feature in the same way that an availability zone is not a proximity guarantee, because those things can also distribute because it's multiple data centers. Okay. So asynchronous versus synchronous replication. And this all comes down to the fact that light is fast, but it's not instant. There's a definite amount of time light takes to travel from one place to another. I can't see it, but it's not instant. And when light travels over fiber, it's about 30% slower than in a vacuum. Well, that means as there's distance, I get a time penalty for as I want to do operations between things, the bigger I spread them out. I can actually look, Microsoft maintains network round trip latency statistics between the regions. So if I'm looking here at West US, how long does a packet take to go and talk to these other regions? So if I look at East US, from West US, it's 71 milliseconds. Now that's still pretty quick. I don't think I would particularly recognize that as my human brain and my human interaction with that, but it's not instant. So now if I think about different components of things talking to each other, if I go to my architecture, if I can find it, like this, for example. So if I have my app logic talking to a database, if they're in the same region, even over availability zones, it might be a 1 millisecond latency. That's fine. I can handle that. But if that suddenly became 70 milliseconds for the most common operations, it would tank the performance of most apps unless it was highly tolerant to latency. So that would definitely be a factor I would have to consider. And realize it's not just even the speed over the fiber. There's switches, there's routers, there's decisions being made. And so I have to now think about, okay, that state I cared about, where do I have the copies? And how does that impact the type of guarantee I can make about losing or not losing data? And so let's pick the two regions. We have these lines of the regions. And let's look at databases. So I'm going to focus initially within a region. Now, when I have a relational database, the key part here is one of them is primary. So I have my database. And in a relational database, one of its fundamental promises is about the consistency and the atomicity of the operations and the ability to roll back all of the things as the part of transaction. So this is durable, it's persisted to a log, then it gets written to the database. But the point here is there's some app, and the app is doing operations. And for now, I'm going to focus on it being an update or a delete or a create operation. If it's read, this is not such a big deal. And I want to think about, okay, well, it's doing something, and I want resiliency for the operation it's doing. So what I would have is within the same region, I have another copy, and this would be a replica, but it's within the region. Even if this is a different AZ, which I would want, it's still really quick. Like maybe it's a millisecond of latency. So what I'm going to do here is when the app makes an operation, I want to ensure that change has been persisted to the replica before I tell the app, hey, I've got this. So this is going to be called a synchronous replication. So the app says, hey, I want to do this operation that's this change. This change will actually get persisted to the replica. Then this says, yes, I've done it. So it's kind of operation 1, 2, and only then it will give the ACK back to the app. So this is synchronous. It makes the change to both of them before it tells the app it has been durably stored. So think what that means is there's no chance of data loss if this instance goes down because it's always been durably stored here as well. So that's why within a region, we always want a replica, and we will do a synchronous replication. And this is going to be the most common type of failure. Something happens to this instance or this AZ. Well, I won't lose any data. I can fail over super fast. This is available. It can be automated. The read-write listener will just be automatically moved to this. Fantastic. Well, now, but I want resilience from if the whole region goes down. So now what I need is the idea of really think of disaster recovery or something in the other. So now I have another copy over here, another replica. But remember what's happening here. In the synchronous, it's a second, millisecond. To persist it here, I'm willing to take the hit of a millisecond for the durability guarantee of not losing data within the region. This is maybe 70 milliseconds. I am not willing to take the hit of 70 milliseconds. So here what we have to do is something called an asynchronous replication. So now when the application makes its operation change, it gets durably stored here. It would get durably stored here as well. And then it would get the ACK back. And then in the background, now it gets replicated over and stored. The benefit here is it's not impacting the performance of the app because it just has to store it here, acknowledges it, and then as quick as it can, I'll go and replicate it over there. But realize in an unplanned scenario, what does that mean? Well, it does mean there is a chance of data loss because if I've durably stored it, I've acknowledged it to the app, and then this goes up in flames, this region goes up in flames, and it's not copied these few minutes of data maybe yet, that data would be lost. So in an unplanned scenario, that's where that recovery point objective comes in. There is a risk of data loss. Now you'll have people say, well, I want synchronous over to here. It's easy to say that. The reality is almost nothing a relational app would survive that. It's just not going to work very well. Now, remember, these are not wasted. These replicas, what actually happens is you have listeners. And so I can have something called a read-write listener here and a read listener here. So I could run analytics against this. This is also could be a read listener. And so what I could have is applications could be leveraging the read replicas and then only have to actually go and talk to the other replicas if then it's going to do a write, for example. Like that would then come into some construct above that. But just realize this is a nice thing that you have. And we'll talk a bit more about the app architecture in a second about this. But that's the difference in the replication. So if we go back to the slide, build all this out. If I can find my cursor for a second. So synchronous, they're committed on the primary and that replica before they're acknowledged back. It could impact primary performance, but there's no risk of data loss. I do that within the region. Asynchronous, we acknowledge it before we go and send it to the asynchronous replica. It means there's no impact on the performance, but it means there is a risk of data loss in an unplanned failover. So we do that between regions. And that's really the core point of that. I'm going to come back and look at that in a little bit more detail in a second. So understanding how do Azure resources actually use these constructs. Now understand, some Azure services are global. They handle their resiliency across even regions. So Entra ID is a global service. Azure Front Door is an Anycast global service. Traffic Manager is a DNS global service. DNS zones, private and public, are global resources. They're replicated. When you use things like GitHub for your store, that is a global service as well. So those are just handled for you. But most resources are actually regional. And I may actually get to pick what type of deployment I want. If I do a regional deployment, it's deployed somewhere out in the region to a cluster. I don't know, maybe in an AZ if it has AZs. I know nothing about it. If it's zone redundant, well then it's distributed over multiple availability zones to give me resiliency from any particular type of failure. If it's zonal, then it's deployed to a specific availability zone you specify. And sometimes we get a choice in this. So if we go back to our picture for a second. So if my service was regional, well, it just gets deployed somewhere. I have zero clue. It goes somewhere. If I pick zone redundant, so zone redundant, it would be spanning the availability zones. Now realize, if I pick zone redundant and I get to pick the number of instances, if you say 1, you're not zone redundant because, it exists in a place. I need at least 2 instances, ideally 3, for it to actually be zone redundant. If I do zonal, it exists in a specific availability zone. And you may wonder, why would I ever want to do zonal? What I would typically do there is maybe I've got a cell-based architecture for my solution, and I would deploy an instance to this AZ. I would deploy another zonal instance to this AZ, maybe another zonal instance to that AZ. I would have some then balancing solution to distribute between them. So overall, I am zone redundant because I have lots of zonal deployments that give me that resiliency. Now, some will give you a choice. Azure Kubernetes Service, AKS. I can be zone redundant because I can tell it to use multiple AZs, or I can tell it to just be zonal by telling it to use one AZ. Storage accounts. I could pick locally redundant, and I'd have 3 copies of the data in a particular cluster. I can pick zone redundant. The 3 copies of the data would be distributed over the 3 availability zones. If I have a scenario where something has to be single instance, so think relational databases again, where the writable, the primary, has to be in one place, what I would do here is that primary, sure, would be in a particular AZ. This replica would actually be over here. It would be in a different AZ, so I'm still taking advantage of those constructs. Make sure in your architecture, everything is at least the same minimum level. For example, I wouldn't want to build these fantastic zone redundant services and then have like a basic, doesn't really exist anymore, but I did some kind of resource that existed just as a regional level or in an AZ that it depended on, well, because now I have a single point of failure. NAT Gateway is a good example. NAT Gateway is only available as a zonal resource. So it would be no good having a nice zone redundant AKS node pool in a subnet, and then that subnet relied on a NAT Gateway, because if that zone was down, none of them would have any network communications. So in that case, I would have to architect accordingly and probably create separate subnets, align the subnets logically with particular zones, and make sure I don't have any cross contamination. I don't want something in AZ1 relying on something in AZ2. So I always want to think about understanding all the different constructs and making sure I'm following the best case and the best architecture principles for those things. If it's a PaaS service, look at the options available to you. Again, with PaaS, I'm pushing a lot of the responsibility over to the service, but there's still certain things I have to understand. So don't have cross-resiliency dependencies. It's a bad thing, and often it's going to trip you up. So I want to talk about multi-region deployments, because for real resiliency, I have to be in at least 2 regions. And one of the challenges we have with that is, what is my app architecture now? Is it active-passive or active-active? That's going to be driven a lot by my data model. And there's certain complexities that absolutely get involved when I try and do this. And you may kind of wonder why. So it's easy to draw this out. Now realize, remember, Azure, I pay based on the resources I'm using. So if I had 6 instances of a tier here, or 3 here and 3 in another region, my cost is basically the same. So it's not so much a resource cost issue. But imagine I have my application. So I've got my app. My app has to talk to the database. It's in the same region. So it's quite happy to go and talk to the read-write listener for both the read. So all the writes always have to go to the primary, and it could read from the primary, or actually more likely, it would probably read from this replica to minimize the workload on the primary. Now, there is it's not that simple. If I'm an application and I just did a write, if I'm in the same region as the replica, I know it's synchronous, I'm good to go. But now imagine I'm an application instance, I'm active, running in this region. What does that mean? My reads can come from this copy. But if I write, I have to write to the read-write listener over here. And that's generally writes a tiny portion of the amount of work you're actually doing. So I'll accept that latency. But realize the app has to be aware of this, because imagine it does a write and then it instantly tries to read the data that it just wrote. It wouldn't have replicated there yet. So there's a certain set of logic I would have to do to say, okay, if I've just done this and I must have that data, either I have some internal cache or there's some other cache going on here that handles that, or I need to make sure I read it back from where I just wrote it from. So it's not as simple, which is why when you get into having a relational database and I want to be active-active, my app architecture has to start considering, well, okay, how do I actually want to do this thing? But it's useful to have these replicas. Again, my analytics I can offload. If this site went down completely, I can promote this, and this would now get the read-write listener. It would then have this capability to be used across that. So that's definitely something that we can do in those multi-region scenarios. Now, sometimes you will get a customer say, no, I want the database to be active-active. There are certain technologies that let you do active-active and multi-write replication for a relational database, but it's very complex. You're having to pay the penalty somewhere. Like, it's not magic. There's going to be a write replication and a write lag introduced as part of that. Also, how do you handle potentially if there's now a conflict between them? The promise of a relational database is it can roll back all of the operations related to a transaction. Or what if bits of things were done in different places? Now I have to handle conflicts. So generally, you do not want to have a multi-write. When someone says that, generally they're not honestly really understanding the promise of a relational database. If I want multi-write, what generally I want is a certain consistency within a session, and then they can eventually be consistent. I want to make sure people see the same set of transactions in the same order over here and over here. So the solution there is there are no SQL solutions. So not only SQL. And with not only SQL, what I can absolutely have is read-write in multiple locations. In fact, Cosmos DB is the solution for Azure. I could have a read-write instance in every region in the world. But what I do is I get to pick the consistency. So very often it's going to be a session consistency. So I see the same things within the session. And then what it would eventually do is get an eventual consistency between the various copies of them. So I kind of get the best of both worlds. I can read and write to my local one. Remember, NoSQL is going to be documents, key value pairs. There's different APIs you can hook into this thing, but it doesn't have those same promises around the acidic nature of a relational database. So just understand there are options available, but my application would need to really behave accordingly based on what those requirements actually are. Don't forget about other dependencies you have. Remember, hey, if there's certain images I report, well, the Azure Shared Image Gallery supports replication. My repositories should be globally replicated anyway. There's probably going to be some kind of load balancing going on between these things. But don't be wasteful. Let's go back to the slides for a second. Ensure all of the core elements are available in all the regions. Don't be wasteful. So if I have a storage account that's got blobs and I'm replicating the storage account through maybe the application, do I need the storage account to be GRS? I'm just doubling the cost. So understand where is the data and state already being managed and handled, and don't replicate for the sake of replicating it. Some resources cannot move between regions. So a public IP is locked to a region. I would need some sort of balancing capability, which I'm going to need to balance between the regions. There's a whole bunch of different solutions. Now, I don't want to go into the detail of what all of these are, but at a super high level, like imagine they're the entry points. An app is generally not talking directly to the database. You generally wouldn't want that. I'm a service, I might use the database, but I'm going to expose some API that things actually talk to. So different solutions available. I'm the client. A basic one is to use DNS. So these have different DNS names. They're in different locations. One of the things we have is something called Azure Traffic Manager. And all it really does, but what it does is it has the different possible endpoints it can use. It exposes its own DNS name. So the client resolves this name, and then it will go and resolve. There's different distribution mechanisms it has. One of them is performance-based. So it would resolve the one that is closest to you. So that's just DNS, and that means it will work with anything. Another solution would be Azure Front Door. So Azure Front Door uses Microsoft's global network, and it has these points of presence all throughout the world. Go away. So this is Azure Front Door. So Azure Front Door is a layer 7. So it understands HTTP, HTTPS, HTTP2. And one of the nice things, because it understands that, this is an Anycast IP. And Anycast means the IP address of this service is actually being offered from every single one of these points. So now I, as the client, I want to talk to this service. Well, I'm going to talk to the one closest to me, and it will establish the TCP session, and then it will establish the TLS session, all against that local point. It's not having to go back to those back-end resources. And then again, it will go and get the traffic from whichever one is closest that is healthy. They're all doing health checks. It will then also cache things. So it's combining the features not only of a load balancer, but of a content delivery network. And because it's doing these communications, I'm going to get this split TCP. So it terminates locally, can then go and get big chunks and cache it. It's going to actually improve the overall performance as well. So that's a really nice solution for the layer 7 things. Within a region, I normally use a load balancer, but it's regional. Another solution we have, let's say it's a layer 4, for example, we have a global load balancer. So a global load balancer, again, uses an Anycast IP. And it then points to regional load balancers. So there'd be kind of regional load balancers for each of them. to give me that global balancing between those. Remember, I could do things at the client. I could have a whole bunch of DNS entries responded. I could remember last IP I used. There's a whole bunch of different capabilities. But as soon as I have those multi-region scenarios, I need some global balancing solution to actually make it useful. I need something to go and distribute those requests among them. Use infrastructure as code. Remember, another type of DR may be to build it out again, especially if the data was replicated. So it helps ensure consistency. It's going to enable you to rebuild. If every resource I have is documented really as code and version controlled, at any time, I can just rebuild that environment. I know it's always going to be the same way as opposed to some human being clicking the right options in the portal. And it gives me that ability to maybe, if I have a long enough recovery time objective, I'll just recreate the stateless bits when I do a failover to save me money. Why have a bunch of VMs or AKS node pools if I'm active passive there if they're not doing anything? They have no state. Why bother? I would rather just create them as I need to. Now remember, if I'm creating them as I need to, do I have a potential risk of, if it's a true disaster, everyone trying to create in that region at the same time? Which is why I would want that idea of regional flexibility, maybe not using that paired region. That gives you that greatest chance. If I absolutely have to have a particular SKU in a particular region, I would probably actually want a capacity reservation and just have the stuff running because I'm paying for it anyway then. So that's a completely different conversation. But I want consistency between them, and Azure policy can really help drive that. What is the preference for replication? I've talked about a whole different things here. And it's probably easy to just look at all of them for a second. If it's available, a native capability of like an application is going to be the best. SQL's built-in replication is going to be better than replicating within the operating system, which is going to be better than replicating maybe some storage level capability. A domain controller's multi-master application is going to be better than replicating at the operating system. Now, there might be a cost difference. Realize that the more up the stack I move, well, I have to have the resource running in the other location. So I'm paying for the compute. Some kind of native replication or in OS to just a disk, I don't have to have the compute running in the other location. So it's going to be cheaper. So it can vary depending on exactly what I need. But you don't want this last one. And not having anything and leaving the industry in disgrace. Not recommended, not a good thing. And I don't have to pick one. So the whole point of what I will do is pick the one that makes the most sense for that particular type of technology, for that importance. Like my SQL database, hey, this is super important. I want replication going on. I'll pay to have the instance running over there. It's worth it. My domain controllers, I don't want to risk losing identity information. I'll have a replica over there. It's using multi-master application, great. This other thing is not as important, but it has some state in a VM. I'll replicate the VMs to a disk. Maybe it's like a 30 seconds or 5 minutes. It would take longer to start up. I may lose a little bit, but it's less important. This other stuff, I don't even need it until it's a DR, and it's a time entry system. It can be down for a day, or I'll just recreate it over there. And again, only its database bit would actually replicate. So I would think about all of the different components of it, and then use the one that makes sense based on the cost. I don't have to do all of the same. I don't want to do the top possible for everything. Use the one that makes sense for that particular requirement. So remember, for your non-stateful components, if you're not running active, consider what is your recovery time objective. Can I just create it as required? But again, remember, I have to be able to go and create the resources over there. If I can just create it when required, use infrastructure as code, use a pipeline. You can automate those things to create it. But how critical is it? As I mentioned before, you do have to remember if there is a true regional disaster, especially if I'm using the paired region, everyone is going to do a run on the bank scenario. Everyone is trying to create stuff. The more regional flexibility you have, the better there. So that would be a real key thing to think about. if I have to be in a certain region, have to have a specific SKU, again, I would probably want to think about on-demand capacity reservations. I'd probably want to think about having that stuff just running. And just make sure you have all the required artifacts. It's no good saying, well, I'll recreate it over there, but I forgot to replicate my image gallery, or I forgot to replicate whatever it is. Your GitHub repos, your Azure DevOps repos, they're replicated sort of globally or within your region automatically anyway. Maybe I can even recreate images. If I'm using Packer type, the Azure Image Builder, I can maybe just recreate it, but it takes time. Again, what is my recovery time objective? How much flexibility I have to actually handle those different types of things. So there's not a right or wrong, but it's really important to understand your requirements. Sorry, voice going a bit. Okay. What about regular virtual machine replication? You probably still have some regular old virtual machines that maybe I want to add protection for. Maybe they're on premises on a Hyper-V box or a VMware box. Maybe they're in another cloud. So from on-premises to Azure, there are different solutions available via Azure Site Recovery. Now, Azure Site Recovery is free for 31 days per machine. If I'm actually doing a migration using Azure Migrate, I think it's 180 days. So I get a much longer time. There's Hyper-V VMs, which is going to use the Hyper-V replica capability with a little host provider. Then there's VMware or physical servers that use a replication appliance and mobility service. For all of these, the VM is not actually running in Azure. It replicates to a disk. And so I just have to pay for the disk cost and then the ASR license. That's likely going to be cheaper than actually paying for the compute. So to draw those solutions out, where do I have space? Where have I got left? Okay, we'll go over here. So if I think for a second, we'll do the Hyper-V first, because obviously that's by far better than anything else. So I have my Hyper-V for hypervisor. I have a virtual machine, and the virtual machine is using a virtual hard disk drive, VHDX file. So what Hyper-V replica does is it looks at the changes and it stores them to a Hyper-V replica log file. We've added some stuff to the Hyper-V server. Now what's going to happen is using the Azure Site Recovery license, which again, if I'm using it for long term, there's a license price for this. It is replicating this up into a VHD file in Azure. So this is Azure. And this is every 30 seconds or 5 minutes. And obviously I'm paying for the disk. So I'm paying for the license, I'm paying for the disk. There is no VM running here. What actually happens here is if there is actually a failure at time of failover, then it will go and create the VM, which will attach to this. And then obviously I pay for the compute charge while it exists. So it's going to create at failover. So that's the Hyper-V scenario. Then we have the concept. I don't know how to draw a sad color, but totally objective about this, obviously. So now imagine I'm on ESX or I'm bare metal. So what we have here is we have the operating system. And the operating system, if I think about the file system, you have a volume driver, you have the file system, and you have the app talking to it. So what this does, it has a modern architecture where you have this ASR replication appliance. So what I have here is an ASR replication appliance. And there's a mobility service gets installed between the file system and the volume driver that as changes happen, it sends it to this, which sends it to a VHD. Now this is continuous. Doesn't mean it's real time, but it's kind of just an ongoing. It's as quick as it can. It's sending that stuff up. And again, only if there's actually a failover will it create the VM, attach, and once again, I'm paying for the ASR license and the cost of that storage. Now, because this works on bare metal, I don't know why I did BA there, bare metal. I'm sure there was some logic to me doing that. It would also work for VMs in other clouds as well. The problem is the failback is only to ESX. I cannot fail back to bare metal. I cannot fail back to a VM in another cloud. So that's something to understand. And again, Azure Migrate uses a very similar thing, but it doesn't care about having to fail back. So it has some additional flexibility in what it can actually do. Now, another VM thing I may care about is Azure to Azure using Azure Site Recovery. And it's really using the same technology as it uses for ESX and bare metal. So it's using the mobility service via an extension that gets installed into it automatically. And I can also put multiple VMs in something called a consistency group, which means all of the snapshots, the point-in-time views, both crash and app consistent, would be the same. So think of crash consistent as if I just took the power out. It's just the point-in-time view of the disk content. App consistent actually flushes out changes to disk. For Windows, it uses the volume shadow copy service to flush the changes to disk, quiesce any changes, take the snapshot, resume. For Linux, there's pre and post kind of scripts it can run to get that capture. Azure Site Recovery also has recovery plans to automate all of those different things. So I'm not having to manually run a 100-page document in a true disaster. I click the button, and then it says, we'll fail over this group, wait, request a human to do something. When they click yes, okay, now perform a SQL failover, now fail over this replication group. It does all of this for you. And so absolutely, if I have state in virtual machines, I can use Azure Site Recovery. And what it's going to do is, once again, imagine I have the VM. And once again, it has the OS and it has all of those other things. It's going to put the mobility service in it. And that's going to replicate to a VHD, which could be a different availability zone or a different region. And then once again, it would go and create the VM if I did the failover, and then I pay for the compute charge of the other VM over there. So there's a lot of different capabilities that you have available. That's the VM world. I mean, ideally, you're using PaaS solutions. You've shifted a lot of responsibility over to someone else. But if you are in that VM world, there's still really nice solutions to handle where you have state that you actually care about. As I kind of mentioned, we don't pick one. I mean, I've covered this a lot. I mean, realize some things you don't have to do anything. If I'm Office 365, it's managed for me. I have no responsibility there, really. And the goal is we try and shift as much as possible. But certainly, we pick the highest one for each of the elements to meet the requirements we have. It's better to have the best and appropriate solution for each type than using some lowest common denominator. So, well, I need to replicate some VMs. I'll just replicate everything with the VMs. No, if there's SQL in it or DC, I should probably use that. So use the right service to get the best capability. And that means there are some extra considerations, but I can automate this. The recovery plans that I have with Azure Site Recovery can still do everything I need with really kind of a single click of the button. There are cost implications. I mean, obviously, if I'm doing something in VM and I'm replicating the app, I have to have a VM running on the other side. So there's a compute charge concept to that. If I'm using a PaaS service and I turn on HA, there's generally another instance running. There's a cost element to that. But it comes down to those recovery time objectives you have, what you're prepared to accept, that will drive what is the best solution actually for you. As we kind of wrap up from a resiliency, you may have the need to actually create clusters in Azure VMs. So maybe I've got some more legacy solution. I've just lifted and shifted it into the cloud, and it needs a cluster. Like SQL, I need a cluster for those SQL always-on workloads. There's some complication added in Azure because I can't move an IP address between things simply. I can on-prem, I can't in Azure. And so we have different solutions. So what we used to do was we'd put a load balancer in front of the instances. The load balancer would own the IP that was associated to the virtual network name of whatever the service was. And then the load balancer would have a health probe to detect which instance it should send that traffic to. So that's what we had to do. But then what happened is in Windows Server 2019 and above, you now have this distributed network name, a DNN. So instead of the cluster name object, we have this distributed network name. And what happens here is that all of the nodes, they get mapped to from that distributed network name. And so it's binding to every IP address of every node in the cluster. The client can then utilize that to find the active node, and it just works. So I don't have to do that load balancer thing anymore. I can leverage that instead. So there's different options. And some of the reasons we see these enhancements in the technologies is specifically to enable some of these Azure scenarios. There's also ways to speed up. There's something called multi-subnet failover that enables the client to connect to multiple instances instantaneously. So it's just, there are some nice capabilities. So where I have to do clusters in Azure, especially for SQL, look at the capabilities that are available for you. Often a cluster needs a witness. Again, something nicely added was a cloud witness. This is just using an Azure storage account. It creates a blob file that can be read to and written from, and it gets locked to help someone grab the quorum to get the vote if there is this split. And it's just the name of the cluster's unique ID. So that's a nice way. If I have like 2 regions being used, and I want to pay for a 3rd region to run resources, I could just create a storage account in the 3rd region. And in the case of a split between them, only one of them will be able to grab the vote of the blob storage file by locking that, and it would make the quorum. It would be able to offer the service. This is all about when I'm using kind of the failover cluster instances that has shared storage. If I need that, well, there's a shared disk capability in Azure where multiple nodes can connect to the same VHD file. There's also Azure Elastic SAN that offers via iSCSI the ability over the network to go and connect to some kind of shared storage. But ideally, go back one. But ideally, try and not have shared storage. Like another option is to use always on availability groups. So what that does is it replicates the data to each node. There is no shared storage. And that's generally what we like in the cloud. Try and avoid having those shared components. It's a much better option for you to use. So where you have the choice, don't have shared stuff, and just let it replicate between the instances. Okay, so then we did mention backup before. So at the simplest level, Azure provides backup services. There's actually 2 mechanisms. There's Recovery Services Vaults. This was the original. And now there's backup vaults, which are used for some of the newer services. We can actually see these if we jump over for a second. One of the nice things we have is now this Continuity Center. So if I go to Business Continuity Center, and I just go and look at my vaults, and I try and create a new one, it will ask me what I want. And it shows you the workloads. So the original Recovery Services Vault is a lot of the original workloads. The newer capabilities we see in the backup vault. So you get to pick, well, based on the workload, this is the one you're going to use. Now, one key point here is depending on the technology, for some of them, the technology has its own native kind of snapshot or replication to a storage account. And the backup service is just acting as an orchestrator to create those things and purge them down to a certain number. For others, it will actually be copying the data to somewhere else. Like PostgreSQL has a PG dump capability that gets spun up on a worker role that writes to a managed storage account that gets written to a block blob, and the Azure Backup just orchestrates that stuff. So there's different options. Largely that's invisible to you. You don't care. The thing you want to make sure is it's calling at these particular points in time. Many Azure Backups, VM extensions can use these capabilities. It can use it on-prem as well. For Windows VMs, for example, it can be app consistent. It calls volume shadow copy service. For Linux, it does the pre and post backup scripts to, again, get app consistency. It's going to use Delta-based storage as much as possible. So it's only storing the data that's actually required as opposed to a complete backup every time. You get to set the retention settings. So I define a policy and I can say, well, how often I want it to be taken. And then I need to keep a daily for X amount of time, a weekly, a monthly, an annual. You have a lot of flexibility in that. Again, if we jump over really quickly and we look at the policies. Now, the exact options will vary depending on the workload. Like if I look at a protection policy and create a backup policy, and let's say I do it for VMs. So I select the vault I'm going to use. Then you'll notice I'm telling it when I want it to back up, but then I set these retentions. So how long to set a daily for, how long to keep a weekly for, a monthly for, an annual for. So I can be less granular, but I need to keep an annual one for 7 years or something, a monthly one for 12 months, a weekly one for 8 weeks, a daily one for 14 days. So I have a lot of control over exactly what I need to do in those various different scenarios. So that's a nice capability with the backup. The vaults themselves, they have different replication of the content, so I could have that storage over different zones, maybe even geo-replicated. And one of the nice things you can do with the geo-replication is I can actually do a cross-region failover. So even if the original region isn't down, I could still restore to that paired region. And as we saw, the Business Continuity Center just provides a single pane of glass that's focused on the workload over kind of all of your different environments. Final thing I wanted to touch on is protecting your backups. Because especially in this day and age, if someone's attacking you, they're going to try and remove your backups. Now, first, make sure people only have the absolute minimum level of permissions. But you're still going to have a backup admin. And if that account is compromised, that won't help stopping someone going and removing your backups. Now, if you have PIM and they have to elevate up and maybe have a required step or a stronger MFA, it would help. But again, if the attacker compromises your backup admin, then what do? They're going to go and remove those backups. Now, there are things we have native to Azure Backup, like Azure Backup has a soft delete option. So it's even if I delete a backup, it's there for 14 days, and that's free. I can then recover it. After 14 days, it's purged. Now, I can disable soft delete via the properties of the Vault. There's also an always on soft delete. If I turn on always on, it cannot be disabled, so it's an irreversible thing. I can extend that soft delete up to 180 days. Now, I will pay for the additional storage past the initial 14 days, but now I have it even longer. So if someone does to go and delete my backups, well, I can go and get them back. So there are some nice capabilities to help me with that. But multi-user authorization can protect if my environment is compromised. So now what I'm going to have is a separate identity completely responsible for a lock, a resource guard. And I have to get a temporary permission as the backup admin on that resource guard before I can do any kind of critical operations. Now, what's nice here is this resource guard can be in a completely different environment, a different tenant, different subscription. It definitely should be a different subscription at minimum. And ideally, even another tenant is really nice here. My backup admin should not be managing this resource guard. Remember, the whole point of this is it's trying to protect me from those bad things. So I'm going to have a separate role that will be granted to the backup admin in the time they're actually going to go and use this thing. I'll talk about that in a second. So let's look at how this is actually going to work, because this is kind of fun. So I've got my backup admin. My backup admin has permissions on my backup vaults. Now, again, it should be minimum permissions as often as possible, but ultimately they're going to have permissions on this thing. It's just they're going to have that. So what's now going to happen is a completely separate identity, my security admin, they're going to create a resource guard. And the whole point here is this should definitely be a different sub, but it could also be a different tenant. And the point of this is the security admin is the one who has all of the permissions on the resource guard. So it's a different identity from this person. Because if this person is compromised, I don't want them to have permissions on the resource guard automatically. Now, once this is created, now the backup admin, they have to have read permissions on it. The backup admin will apply the resource guard to protect it. So now it's protected by this resource guard. If the backup admin now wants to do any kind of critical operation on the backup vault, what they actually have to do is temporarily get a permission. So this could be a privileged identity management, which they would have to authorize. They would have to go through some other checks. Another human has to check it. They temporarily get this permission to perform the critical operation that would maybe reduce its protection or delete protection. And then they can do it. So this other thing has to be involved. A completely separate identity would have to be complicit or compromised as well before they would be able to do this operation on it. So that's like the key point. It does have to be the same region. That's the only thing to consider, but it's different sub, different tenant, all would work fine now. So that this is a really, really nice capability to leverage. And you also have immutable vaults. So the point of immutable vault is what I can do here is there's different levels of this, but the key point of what I can say is that think write once, read many. Once I lock and make it immutable, you cannot delete it before the intended expiry time. So initially I can enable the immutability, but it can be disabled. But once I've tested and I'm comfortable with the settings, I can do an enable and locked state for the immutability, which means it cannot be removed, no matter what permissions you have. So you want to be careful before doing that, because imagine you enabled and locked it and I had a really long retention time. Well, that cost me money. So make sure you understand what that retention, the cost element is, because you cannot undo it once you do that immutability. So I then can't change the policy. I can't shorten that retention or anything else. I can't stop the protection. I can't delete the data. That will protect that thing. So just be really sure of those settings before you go and do that. And yeah, I mean, that's a combined these things together, the immutable capability and having that multi-user gives you a really strong backup posture. And that was it for the resiliency module. It's gonna hopefully tomorrow will be better. Hope that was useful. Until next video, take care.